Okay. Hello, everybody. The subject of the lecture today is to introduce you to linear regression in machine learning. At first, I wanted to pay your attention to the definition of regression according to Webster Dictionary. There it is written, regression is a trend or shift towards a lower or less perfect state. Really, if you look carefully at the different definitions of regression, you may not discover this meaning very easy. Let us try together. Here is a definition. For example, linear regression is a broad concept referring to modeling relationships between variables by using linear equations. Where is the shift and how is the shift towards lower or less perfect state? It is not seen here. More precisely, the term linear regression means to find linear relationship to describe the correlation between an independent and a dependent variable. Practically the same words. Another similar definition. It is also defined, talk here is about regression, as a statistical technique used to find the relationship between variables. Regression analysis uncovers the associations between variables observed in data and so on. In statistics, a statistical method, it is defined as a statistical method that tries to determine the strength and character or trend of the relationship between dependent variable and a series of other variables. So, as you see, all these definitions are very close to each other, and the essence of all of them is that there is always independent variable or variables, and there is one output or one dependent variable, and we want to find the linear relationship between them. To find the linear relationship means that we can define an equation, a linear equation, where we have the variables as input and output. Such a line here, this line is a linear regression line. And as usual, the line is always easy to define by a simple equation like the general equation which we used in school, y, which is the dependent variable, is equal to the input x here, which is the independent variable, multiplied by a coefficient m plus a term, constant term called b. This is the general form of a linear or a line or a linear function, which could be used as a linear regression function. The coefficient m usually is referred to as the slope of the line, and b usually represents in mathematics the intercept or the bias value when x equals to 0. So if you go back here to what I have written to you, we have an independent variable x. We have a dependent output variable, which is y, because for every x value, we have a corresponding y value. This y value at the output with a hat. It is defined here as the predicted value. Predicted value. What does this mean? This means that if we have a set of values, these black dots, and usually this data set is huge and of a great number of points. And each point here is defined, the coordinates of each point is defined by an x value and a y value. The x is the input, y is the output. We find here for each value of x, for each point, there is a value x and a value of y. The question here is if we want to examine this data set and to make use of it in real life, by using statistical methods, we can really derive some concepts which enlighten this problem, such as the mean value, for example, or the standard deviation value, the variance, and so on. But really, it is still difficult for us to make use of these points directly in order to define for every input value what is the corresponding output value. We cannot do that directly, even by statistics. So regression is used to solve this problem. How? We have to think or to assume that there is a line, such this line, which is considered the best fitting, which represents the characteristics of whole the set of points here. Really, this is a very difficult thing to do, because as you see, if I take a value of x here as input, really I can get the output, which is the predicted value, y with a hat. And for another x, I can get an output. This is estimated output, predicted output. But this output is far away from the real values. If I take this x, as you see here, and I found this value on the line, which is the predicted value, but the true value really is this point. So there is an error always. In 99% of cases, there is an error or a difference between the original true value y of this point and the predicted value. This is called an error. And this is common for any point of the points in the data set. So when we assume that this line is a descriptive and really it maps the general characteristics of the whole set, really this process is associated with degradation of the information. Here it comes now, as Webster has said, that it is a trend or shift towards a lower or less perfect state. So when we make regression, we usually have errors, have differences between the true values and the regression line here, which is taken as a mapping for the x and y values, or the relation between x and y values. So for every point here, there is an error. Sometimes it is called residual. And in machine learning also, the intercept point here, which is this value, is also given another name. It is called the bias here. And the value also of the independent value here, x, it is called in machine learning as the feature, and the output value, y, or the estimated value, it is called as a label. So here, in simple terms, linear regression in machine learning is a way to find the best fitting straight line through a set of data points. Why we use that? In order to be able to predict values, labels, when we have definite values of the features. This line helps predict a value based on one or more input factors. This is the idea behind this definition. I hope now that it is more understandable by all, and we shall continue our work. Yeah. Let us, here is an example, for example, how we relate the independent variables and the output variables using a linear relationship. Here, an example is taken is the results of an exam score, for example, and how it depends on the hours spent on use for studying the given subject. So here the hours are considered as the input, or as the let me say the feature, and the label here, or the output, or the dependent variable, is the score of the exam. So the independent variable, or the input, or the feature, is the hours studied, while the dependent variable, which is the output, is the exam score, or what is called the label. So again, if we want to write this in a linear manner, so y with a hat, y it is with a hat, now I shall tell you, is equal to theta 0 plus theta 1x. Y is the predicted value, which means this value which lies on the line, and because any value which lies on the line, the regression line, is not exactly the true value, so it is an estimation, it is a prediction, so it is a predicted value, and given with hat. Theta 0 here represents the intercept, or the bias. Theta 1 is also representing the slope here, the slope of the line. In machine learning, it is considered as a coefficient and given a name called weight, a weight, and x here is the independent input variable. So if you remember this expression or this expression, they are exactly the same, but this is a mathematical expression, and this line, of course, is not a regression line. It is a general linear line, a general line not used in machine learning. If you use it as a regression line, of course, you have to show that this is a predicted value, an estimated value, which is not exactly the same as with the real values. Of course, again, you can give many examples like this, like the dependency of the salary as an output based, for example, on the years of experience. So this is another example here, with this value represents the intercept or the bias, and the tangents of the angle theta here represents the slope of the line. This line is the regression line, y equal theta 1 plus theta 2x. Of course, y here should be with a hat. Any point here should be with a hat. And here also, we can show that if you look or examine the independent variable xi at this point, you find this is the value, the predicted value of the output, which lies on the line, which is given index y pi, predicted value I for as a point index I. But in reality, the point with red here is the true value in the data set. So the distance between yi and y predicted I, this distance here, or as it is shown here at this bracket here, it is the error, as we have said, or the residual error. So shortly speaking, up to now, we can say that we can assume, we can always think that we can map the relationship between the independent variables and the dependent variables as a linear relationship. Because it is linear and because this line does not represent exactly the same information which is in the original set, it is called linear regression. Linear regression also could be linear with multiple variables. Instead of having an input variable x, we can have x1 and x2 and x up to xn, for example. In other ways, we add linear components here as x2 multiplied by theta 2, x3 multiplied by theta 3, and xn. By adding a linear components to the original line, we can get also multiple linear regression method. Of course, also we can talk about nonlinear regression. In this case, we have to add to the linear regression another component which is not linear, like a component of a sine or cosine or quadratic function. So we can have a curvature of the output, which represents not a linear case, but a nonlinear case. Anyhow, for a linear case, y with a hat is equal to the bias again, or to the intercept, plus theta 1, which is the weight theta 1, or the slope, multiplied by x1 plus theta 2 by x2 and up to xn. This is the general form of multiple linear regression. So if we want to summarize what we have said up to now, the goal of the regression algorithm is to find the best fit line equation that can predict the values based on the independent variable. Really, we have now a new concept here, a new expression, the best fit line. If we look at this data sets, which are the red points here, and this is the regression line, really it is difficult to say that this is the best fit, this is the best line which fits this data set. How we can do that? This is an important question because you can assume that there is another line parallel to this line upper to it or lower to it, or another linear line with another slope, and it could be really with the better or in a better manner, it is more accurate for use than the line which is given here. How we can judge that this line is the best fit or better fit? Really, we have to consider, as we told you here, we have to consider the error values for each point, the residual. So for this value xi at the input, I have yi and I have epsilon 1 here, which is the error. And this error is not the same for all the points. For every point, there is its value error or its value of residual error. So how to define the best fit? We define the best fit if the line of regression here has the minimum error or minimum total error, the total error for all the points. But if we consider this point here and look downwards and find another point exactly here, so we can see that there is a positive point and a negative, a positive error, and sometimes there is a negative error, and we cannot take the sum of the errors directly. In order to take in consideration and to be correct, we need to use the square of the errors. In this case, if you square the negative error, you get a positive value. And if you took the positive error, you also working with a positive value. And so now we can have an idea about the sum of the sum or the total error for the points. But this error, as you see, it should be at first squared. So we firstly should find the difference between yi, this is the true value, and yi hat with a hat, which is the estimated value. The difference between them is the loss, or the residual, or the error, or the cost. All these terms give the same meaning. There is an error here. This error must be squared so that we can make use of positive and negative errors. So yi minus yi hat must be squared. And then we take the sum of all the errors for all the points. This is called sum of squared errors. Sum of squared errors. Now we can say that the line of regression or regression line, which has a minimum value of the sum of squared errors, this line will be the best fit. The best fit then now could be defined easily, and really it is a good idea, and it is practiced everywhere in machine learning and in statistics. Very often also, instead of using the sum of squared errors, we can use a more standardized value by taking the mean of the sum of squared errors. Here we have to divide sigma of yi minus yi hat squared by the number of points in the data set. In this case, we are working with the mean square error. Mean square error. So mean square error is calculated by taking the average of the squared differences between predicted values, y with hat, and actual values, y. This is for each data point in the data set. So now I think we understand what do we mean by regression, linear regression, what do we mean by multiple linear regression, what do we mean by the best fit, and how the best fit line is considered through considering either the sum of squared errors or by using the mean of squared errors. Having this in mind, now we can develop our information in this aspect. So we are now working with linear regression, and we want to find the best fit. But the best fit here is tied with the concept of finding the square or the sum of squared errors, and this sum of squared errors must be minimum. So we have to minimize this expression, and this expression now is considered as the objective function, as we did in optimization. So all what we need to do is to optimize the MSE or SSE in order to find the linear or the minimum value of this objective function. And by this, we can say that this function with the given parameters is the best fit. Okay. Now again, so as I showed you in the previous lecture, in the previous part, we find the error E as yi minus yi hat, and if yi hat for every point xi is expressed as m, which is the slope, and it is a constant value m, and b is a constant value, so this expression now represents y hat. So we can put y divided by n, which is n here, the number of points. This is the total for all the points from I equal to 0 to I equal to n. And now we find the error, which is yi minus this expression, which represents the line, squared. So this is the mean squared error, which is the objective or cost function. And now our work is to minimize this function. What do we mean by minimizing this function? We mean by that we have to find the values of the coefficients b and m for which we can get the minimum value of the objective function. When the minimum value of the objective function is achieved, then we have defined for this specific case the value of m and the value of b, which means we have exactly defined the linear regression line which has the best fit. So in order to do that, you will remember when we worked with optimization, here although m is a constant value and b is a constant value, in order to find the minimum of the regression of the objective function, we shall consider m as a variable and b is a variable, and take the partial differential by m and the partial differential by b, and then apply the gradient descent method. By doing that, we can get the minimum, and then we can define the values of m and b, or in other words, we have defined the best fit line. To do that, so at first we find the differential, the partial derivative of the mean square error by dm, here is m, and then we find the partial differential of mean square error by db, which is the intercept in this case. We find these values, and now by having or knowing the differentials, we can use the gradient descent to find the minimum value. Now, in order to find the derivative, dmse by dm, here, look, I have rewritten the expression mse is equal to 1 divided by n multiplied by the sum of I equal to 1 to n with the squared error. This is the same thing as it is written here upwards. And here now, instead of yi, I have substituted it by mxi plus b. And now we will have to take the derivative of this function by m and by b. If we take the derivative by m, here it is squared, we have 2 divided by m. It will be minus here xi, so minus xi multiplied by yi minus mxi plus b. Or you can write it here, 2 divided by I, the sum of minus xi, this is xi, multiplied by yi minus, this is the y prediction. So y minus y predicted here, multiplied by minus xi, for each point, of course, you divide it, you multiply by 2 by n, you get the differential of the mean square error by m. The same approach we do to find the differential by b. It's the same expression, except that we do not have minus xi here. Yes? And now, if we want to rewrite this in Python, we can say that the gradient by m gradient is equal to, here minus, you can take it outside, minus 2 divided by m, multiplied by sigma is the sum of xi multiplied by the difference yi minus y predict. And the differential also with the gradient by b is having this expression exactly the same as above here, except that there is no xi here. We have the gradient by b. And now, as you remember, by the gradient descent, we usually multiply the derivative m gradient by the learning rate, which is a fractional value and a very small value, and we subtract this value from the current value to get the current derivative, to get the second or the following derivative, and we do this the same for b, and we continue doing that until we come to the number of derivatives which we want, or until we come to the condition where the derivative equal to 0. So in this case, when we come to the end of the gradient descent iterative process, we come to a minimum value of the objective function, which means for these specific values, now the new specific values of m and b, we can say that this is the best linear fit. So as you see, when we work with regression here, to make a summary for what I have said, when working with regression, we at first need to consider the data which we have, and then depending on the nature of distribution of data points, we suggest a linear or quasi-linear mapping function, which is used as a primary estimation. And then this line, now we use its expression, its coefficients, of course, and we find the sum of squared errors for all the points, and or the mean of square errors. And then we find, and we now for this function, which is a convex function usually, we use the gradient descent method in order to find the minimum value, and consequently to define the coefficients m and b for this minimum value or for this best fit. After defining these basic concepts for you, We shall work with Python and we shall work with LabVIEW through examples as we did in the optimization chapter to give you the experience and variety and to acknowledge you with variety of different methods how we can realize regression, linear regression, and also nonlinear regression. This will be done in the coming lecture. Up to that time, wishing you the best and goodbye.